pleasure to be here. It's I want to thank all the organizers, Kevin, Vishnu, Sanjaye in particular, for arranging this wonderful occasion in this wonderful environment to be talking about physics. So I will be talking about some permutation algebras, which I will define, and matrix tensor holography. Primarily, this is based on two papers written with Joseph Mandelstam, who's an expert on tensor models. One is 1307, and another one is archive 1708. So, I just want to describe these algebras. Simplest example of the kinds of algebras I'll be talking about is based on the group Sn. So you take the symmetric group, which is the group of rearrangements of 1 to n, the group, finite group of order n factorial. It has an associative product. You can multiply three things, and brackets don't matter. Now, from the group, you can construct an algebra. So what are these? This is the set of linear combinations where you define a formal sum and you allow yourself to have some complex coefficients, C of Sn. Now, there are n factorial coefficients, so this set of things is a vector space of dimension n factorial. It's a vector space with a product, because you take any of these linear combinations, you multiply two of them, you can just use the product in the group to get, again, a linear combination of group elements times some complex numbers. It's a closed associative algebra. It's also a semi-simple algebra, so it's an associative non-commutative algebra. So associative algebra means vector space with an associative product. We just talked about that. And it's also semi-simple. So semi-simple algebra means that it has a non-degenerate bilinear pairing. So you take two of these vectors, which are in C of Sn, and there's a rule for getting a number out of this pair of vectors. How do you get a number? You take a linear combination here and another linear combination here. How do you define this number? Well, you take the product of these numbers, you sum, and you take the delta function of sigma 1 times sigma 2 inverse. So this is the group delta function. It is defined to be 1 if this is the identity element, and it is 0 if this is not the identity element. So sigma is identity, I write it this way. So you can show that this is a non-degenerate pairing. So it's kind of, if you write it in a basis as Gij, like a pairing, that pairing is an invertible matrix. Now, there's a very general thing which is true for associative non-degenerate algebras, semi-simple algebras. It's called the Wedderburn-Artin theorem. Simplest sign of that in this case is that this n factorial, you can write it as the sum of the squares of the dimensions of the irreducible representations. So that's just a fact about numbers. N factorial, take every irreducible representation of Sn, calculates its irrep, the dimension of that irrep, take the sum of squares, you're going to get n factorial. So for example, S3, you have three representations, symmetric, antisymmetric, and a mixed symmetry. The mixed symmetry has a dimension 2 for 3 boxes. So 2 square plus 1 square plus 1 square is 6. And that kind of numerical or number theoretic fact has an implication. It says that this group algebra is actually a direct sum of matrix algebras. Okay, so for every of these irreducible representations, there is a matrix that you can build. How do you build this matrix? You take the representation, it's a representation, so you have matrices, let's say this is an orthogonal basis, and you have some numbers associated with every group element. Now, if you take a sum of permutation elements, with these DRIJs. This is the matrix for sigma in representation R, and then you form this sum. These have nice properties, these QRIJs I've just defined. It's something labeled by an irrep, and then it has two labels running from 1 to the dimension, so that dr square of them. And these have nice properties. In particular, they multiply like elementary matrices. Elementary matrices, EIJ is a matrix with zeros everywhere except 1 in the IJ. So these guys multiply in a very simple way. And these Q's analogously multiply in the same way. QIJ, QKL is delta JK, QIL.
These are complex matrices?
These in general will be these. Actually, it turns out that for C of Sn, you can find sort of the basis where all the matrix elements are real, so these coefficients will turn out to be real.
Even though the vector space had complex, vector space which you defined earlier had a complex.
That was in general complex, yeah. So, but I'm allowing myself to form complex linear combinations of these things. So that's right. So these are basis vectors, and I'm allowed to multiply them by complex numbers, and I'll get an alternative basis for the same thing. So basically the same C of Sn, which is, so how do we think about functions on Sn? We can think about these A sigmas, which are some numbers associated with group element. So we can have either this kind of permutation type basis for C of Sn, or we can have this, this fancier representation theoretic basis for the same algebra. And these have the nice property that their multiplication is just like matrices. And that's what Wedderburn R10 tells you. Every semisimple associative algebra has this property. So that's the first example, the group algebra of Sn. The other example is the center of that group algebra. So take the subspace of this associative algebra, which commutes with everything in the algebra, it's the center. Commutative associative algebra, take all z's in the center, which commute with everything in the thing, find all z's, all linear combinations, which commute with any permutation, basically. How do we build these elements in the center? One way to do it is you just take any permutation, sum over an arbitrary permutation in Sn, and average. So if you take some average like this, if you multiply from the right, you can redefine the gamma and bring it to the left, so this commutes with everything. This is some central element built from permutations by average. So as you see, your gamma, sigma, gamma inverse is in the same conjugacy class as sigma, so I'm summing over everything in a fixed conjugacy class. Now take S3, just to make it a bit more concrete. So if you have the identity permutation, 1 goes to 1, 2 goes to 2, 3 goes to 3, we're going to write it in cycle notation as 1, 2, 3, 1 to 1, 2 to 2, and so on. This 1, 2 swap, where 3 stays fixed, in cycle notation is a 1, 2 swap with 3 staying fixed, and also written as just 1, 2, forgetting the 1 cycles, which is trivial. And then 1, 2, 3, where 1 goes to 2, 2 goes to 3, 3 goes to 1, I'll write in this cycle notation. Now, for each partition of 3, each way of splitting it into 3 positive integers, there is a cycle structure. And the importance of these cycle structures is that conjugacy classes are directly related to cycle structures. Okay. So if 2 permutations are conjugate, they have the same cycle structure. For example, 1, 2, 2, 3 have the same cycle structure, the numbers are different, but they are the same cycle structure, so they are conjugate. And these central elements are sums like this, sum of everything in the same, with the same cycle structure with equal coefficients. So there are 3 such things because there are 3 cycle structures. And these things form a nice commutative algebra. You can multiply this identity, multiply this by that, you just get itself. 2 copies of that T2 times T2 is some, you can either get the identity, so this is the 3 times the identity, or you can get these permutations. So this is a closed algebra made out of central elements. So it's the center of the algebra. Now, likewise, for the center of Sn, as we said, the cycle structures are given by partitions, which are specified by some number of 1s, some number of 2s, and so on. And this, for a given n, the number of partitions is a famous number sequence, P of n. Now we have the fact that for each conjugacy class there is an irreducible representation. Correspondence between conjugacy classes and irreps. And correspondingly, there is a construction, there's something about the vector spaces in question, this algebra in question. There is a basis of this algebra which comes from irreducible representations. So we have these matrices for every sigma. If you take their traces, you get the characters. If you take sums of sigmas with the weighted by characters, you get some things in the group algebra which is central, which is something in the center of the algebra. So there are nice projectors which are central elements. They commute with everything, and that they have a very nice sort of orthogonal multiplication. So you have PR, PS is delta or S, BR. So something in the center looks like a linear combination AR, PR, sum over R. And this, what has happened here in terms of this Wedderburn-Artin theorem, is we have decomposed the center into a sum of one-dimensional blocks. Each of these projectors spans a one-dimensional vector space, and so this is a general thing, both for C of Sn and for the center of Sn. We have an algebra which can be written as a direct sum of blocks. So, key things that we have just said about permutation algebras in these particular two examples is that they are related to interesting number sequences like n factorial and P of n. These algebras have two types of bases. One is from the permutations themselves, and one from a representation basis coming from irreducible representations. And then there is a structure theorem which says that these algebras can be decomposed into matrix algebras, and that implies that their dimension is always a sum of squares, as we saw. Now, for the rest of the talk, I'll be generalizing, considering generalizations of these algebras, which will be called permutation algebras, and I'll show how they control the counting of observables in matrix and tensor models, both for finite n and for large n. And kind of this representation basis associated with the matrix structure of the algebras, they are related to properties of correlators in Gaussian matrix or tensor models. And as in this simple case, these algebras are related to interesting number sequences, and there's some stringy geometry as well associated with these algebras, which becomes apparent when you look at how to interpret the counting formulas that we encounter in counting observables of matrix or tensor models. So that's the plan. So one basic fact, you say, okay, in tensor models you have some multi-index tensor with a UN. So why is it that we have permutation algebras? So the fundamental reason why is that if you have a fundamental of UN and an anti-fundamental of UN, we are interested in gauge invariant, so we're interested in invariant one-dimensional reps of UN. So if you take V tensor V bar, how many times does the trivial appear? It appears once, and it's basically the contraction. So EI tensor EJ delta JI. So this is fundamental. The contraction gives you invariance. If you have, let's say, little n copies of V and little n copies of V bar, how many times does the one-dimensional representation of UN appear in this tensor product? When the UN is acting diagonally here. So they're n factorial. And what do they look like? Basically, you have the vectors in V, the vectors in V bar tensor n, arbitrary vectors. To get an invariant, you have to contract basically the i's and the j's, but the contraction can be done in any order, which is parameterized by a permutation in Sn, and these delta contractions involve Sn. So if I'm doing UN, capital N, group theory, and I have n-fold, little n-fold tensor product, I will encounter the Sn group theory. And that's the fundamental reason why permutation groups relevant to counting invariants and have these applications that I mentioned. So the outline for the rest of the talk is that I'll start with simple example, holomorphic invariance of the complex matrix, how we do this parameterization of the invariants with permutations. And a key point is that when you do that, when you parameterize invariants with permutations, this parameterization is redundant. But the redundancy can be described in a very precise way as sort of a gauge symmetry. Okay, so there's a precise description of the redundancy which we exploit in arriving at sort of generalized permutation algebras. So at the end of this first section, I'll give you a little catalog of how different algebras apply to different matrix tensor problems. And then I'll look at a particular case of complex tensor models which have been of interest recently in connection, have been of interest in the last several years in the tensor model community, and then recently due to their connections with SYK as well. And then I will, in the third part, I will describe some sort of stringy geometry, which those of you who are familiar with 2D Yang-Mills theory will recognize, and I'll show how that kind of geometry is related, it also appears in tensor models, and it is suggestive of some emergent geometry which I will describe. So, let's take the one complex matrix. So you have one matrix, it's in a theory where you have one adjoint, so Z transforms as U, Z, U dagger. You want to build all the invariant functions of Z. You can organize these functions by degree. Here I have degree 3 functions, trace Z cubed, trace Z squared, trace Z, and trace Z the whole cube. Now, all these traces, as we said, they are invariant things, so they are obtained from the general matrix elements by doing contractions. So you can order the first index 1, 2, 3. These guys are going to be some permutation of 1, 2, 3. Okay? So, so you have, if the permutation sigma is 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 1, then 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 1, is trace Z cubed, because this is how it's contracted. Notice the redundancy. If I take a different permutation, not 1, 2, 3, but 1, 3, 2, then I have 1 goes to 3, 2 goes to 1, 3 goes to 2. Now this also looks like trace Z cubed, but I have to do a little rearrangement. I have to bring this over here. And because these are bosonic variables, there's a sign if they are fermions, but this is bosonic variables, so you bring them over, and then you get the same index contraction, trace Z cubed. So, two things with the same cycle structure, using the bosonic symmetry, give rise to the same observable. 1, 2, 3, 1, 3, 2. And these different things, different fillings of the same cycle structure, are related by conjugation. So the general statement is that I can build any gauge invariant operator by taking the indices and contracting them up to using a permutation, but I have the same observable if I conjugate the permutation sigma with some arbitrary gamma in Sn. This is for the case where I have one type of matrix. Okay? Now, so basically we're looking at conjugacy classes of Sn. And as we said, Sn representation theory says there's a very nice basis for the center of Sn, which is coming from irreducible representation. So that means you take sums of permutations and you take a sum weighted by the character. Now what I showed in the previous pages is that for each sigma there's an observable. There's a gauge in O sigma of Z, there's an observable. So now correspondingly to this projector I can take a sum of these observables weighted by characters. And these observables have very nice properties. They have very nice properties. They've been studied in the context of the half BPS sector in ADS5 cross S5. And one of the nice properties is that if you now do finite n, UN being finite, it's a very simple cutoff on this Young diagram label. The height of the Young diagram is no longer than capital N, and that implements the stringy exclusion principle, and it is used in mapping half BPS gauge invariant operators to giant graviton branes. So basically, the fundamental thing going on here is that there's a kind of equivalence class of permutations. There's a natural transform on those equivalence classes coming from representation theory, and that knows about finite n. And this will be a general sort of story. And why does it know about finite n? That has to do with something called Schur-Weil duality. What is that? So if you have this fundamental of un, so this is a fundamental of un, we know that we can build arbitrary irreps of un by taking tensor products and then looking at symmetry types. If I have a tensor which is completely symmetric, that's one type of representation of un. Completely antisymmetric is another type of representation of un. But more generally, you have mixed symmetries characterized by a Young diagram. So these kinds of things decompose for me the un, this V tensor n, into arbitrary irreps of un. But when you do that decomposition, there are some multiplicities that appear. Schur-Weil duality takes advantage of the fact that Young diagrams have another dual role. If you have a Young diagram with n boxes, you can fill in the boxes according to certain rules defining standard tableau with numbers labeled from 1 to n, little n, and these form a basis for an irrep of Sn. So the same object, Young diagram with n boxes, corresponds to a symmetry type for un representation, and it corresponds to an irrep of Sn. And the precise general statement of Schur-Weil duality is that if I take this tensor product here, I want to decompose it into un and Sn simultaneously, I have a very simple decomposition. I could organize it according to representations of un and Sn using the Young diagrams, and there's a very simple cutoff. The height of the Young diagram is no bigger than capital N. That's the origin of why, when you organize things in terms of Sn, the finite capital N cutoffs are easy. It always has to do with this theorem. So, what we have seen here is that permutations do in matrix, and I just showed it for the matrix, but generalized, permutations play two roles. One is they parameterize gauge invariants, and then another role is that there's a redundancy, and this redundancy is also described by permutations, in this case by conjugation. So in the more general applications to matrix and tensor invariants, what will happen is that you will have a sequence of permutations, maybe living in a product of symmetric groups, and then you have a subgroup which will implement the gauge redundancy, the redundancy in this parameterization. And once you've identified the correct permutation equivalence classes, the correct permutations and the correct redundancies, there's a kind of a standard box set of mathematical tools which involves this kind of representation theory, which gives you a new basis for these equivalence classes. And you can think of this as a generalization of a Fourier transform. In ordinary Fourier transform, you have functions of theta, you use a basis e to the in theta. But e to the in theta is the matrix element for e to the I theta in the charge n representation. So you're using matrix elements of irreps to decompose your functions of theta. So this use of representation that I described before is a kind of Fourier transform, and it gives you nice basis for these equivalence classes. And it also connects to a matrix structure, and there's Schur-Weil duality, which helps you control the finite n effects. So once you identify this fundamental thing, what are the right permutation equivalence classes for a given problem, then all this kind of follows. So I want to illustrate how that happens. So here's a little table. You have, for example, a one matrix problem. You're looking at functions of degree n, so involving n copies of z. So this is a un problem, and there is a discrete group, which is Sn, related to how many z's you have, and there is a gauge symmetry. In this case, it's also given by Sn, and there is an action of this in general, this will be a subgroup of this one, and this action is just conjugation that we just saw in detail. What happens in general? Well, let's say another example. If you take a two matrix problem, let's say I have m copies of z and n copies of y. All the gauge invariants are built by taking a permutation in m plus n, or Sm plus n, where I'm thinking about m copies of z and n copies of y. And then the gauge invariances, which have to do with the bosonic nature of z and the bosonic nature of y, identify a subgroup Sm cross Sm. And then the action of this subgroup on the group is just conjugation. So this allows you to do a lot of very nice things with two matrix or multi-matrix systems, a lot of which has been done, here at WITS by Robert and students and postdocs who have used this kind of thing to study strings attached to giant gravitons and identify integrable sectors and so on. And so this is a very nice way to think about gauge invariance for multi-matrix systems. So what I'm going to talk about today is 3-index tensors. And not kind of too surprisingly, the group G that appears is Sn times Sn times Sn. And there is a kind of gauge symmetry of Sn cross Sn, where this Sn is diagonally embedded here. And this is diagonally embedded here. And what is the action of this? This Sn acts on the left. Gamma 1 acts on the first, second, third. Gamma 1, gamma 1, gamma 1. And gamma 2 acts on the third. And this defines an equivalence relation. Any sigma 1, sigma 2, sigma 3 which is related to something else by this kind of equation. So this triple of permutation and that one for any gamma 1, gamma 2 basically will describe the same gauge invariant. And to know how to come up with this, it's a matter of drawing some pictures. And I'll show you how that's done. And once you do that, a lot of things will follow. And there's a sort of there's also another way to think about these gauge invariants in complex tensor models is it comes with partial gauge fixing of this story. Instead of having Sn cross Sn gauge symmetry, you have just Sn, and instead of left and right, you have conjugation. So, but we'll just think about one of them and try and convince you that that's the right structure. Just as another side remark, I want to say that this two-matrix stuff generalizes to any quiver, and then you have the group G in that case, one for every node, and the H gauge symmetry in this discrete language, there's one permutation for every edge, and this was described a couple of years ago with a student. Great. So for rank D tensors, so this is the problem we're interested in. In fact, this is a problem that the tensor model community was interested in 2013, well, for several years, and my collaborator Joseph wanted to know the answer to this question. And so the question was, if you have a multi-index tensor with D indices, and another conjugate tensor with D upper indices, and I have some, let's say, n copies of this tensor, and then n copies of the 5 bars, how many invariants do I have? So the answer to that is given by taking the group Sn, where at least n is the number of phi's I have in my composite operator. This D is the number of indices I have on each phi. And I have a subgroup H, which is the diagonally embedded, so this is a diagonally embedded Sn. And there's a gauge symmetry, which is H times H, and the gauge symmetry is that you take a D tuple of permutations in Sn, and you impose that that is equivalent to this D tuple where I'm multiplying on the left and right. On the left by one permutation, one fixed permutation, on the right by another fixed permutation. So it's an action of the diagonal left and the diagonal right subgroup. So once you've identified this equivalence class, basically everything you want to know about counting and correlators, well, you know a lot about it. Yeah?
Does it also be independent of whether the D indices, like they have some certain symmetry property between them or not?
So here, there's no symmetry. So we're looking at the case where there's no symmetry between them, and there'll be some variation of this if you do impose a symmetry.
So if you do not have a symmetry, then this multi-index tensor thing is just like the thing that you were describing earlier, some b to the power n for un.
That is correct, yeah. It's just that what is new is that when I consider a polynomial function of these phi's, there will be a symmetry there. Phi and phi, I can kind of commute them. In fact, that's the origin of this gauge symmetry, this H cross H. I'll show you this. I'll skip that for now. Okay, so to identify the right permutations, equivalences, you have to draw the right pictures. So take phi, let's say it's a 3-index case. So phi has 3 indices, I1, I2, I3. So I'm going to draw them I1, black, red, and blue legs coming out of the vertex. That corresponds to phi. So for a phi, I have a vertex. For n copies of phi, I have n vertices. And then, so that's the n phi's. And then I have, for the phi bars, I have n vertices here. So sorry, this is a typo, there should have been a phi bar. And now we have to build gauge invariants, which are un cross un cross un gauge invariants. Has to be invariant under separately this un, that un, and that un. Okay? And that means I can contract the black with the black, the red with the red, the I's with the P's, the J with the Q's, and the K with the R's. And this kind of multi-index tensor models, the tensor model community who've been thinking about this since 2009, they have been exploring double scaling limits of tensor models, and they have realized that this kind of multi-index objects with a gauge symmetry restricted to be un times un times un times, sorry, this is un to the d times d, one for each leg. This is a good thing to do. If you study tensor models like this, if you start with a Gaussian model and then you add some poetic interaction, you can define nice double scaling limits which lead to melonic graphs and so on. So there are reasons to be interested in these models. And here the question we had in 2013 was how to just characterize the general observables. So they are coming from arbitrary contractions of I's and P's, J with Q's, and K with R's. And these contractions, well, we can draw them. All the black strands from the phi's will contract with the black strands from below, but they can be permuted by a sigma 1 which lives in Sn, permutation of n strands, and a sigma 2, also permutation of Sn, and a sigma 3, permutation of Sn. And of course we don't expect that we're going to have n factorial cubed invariants, so there's going to be a redundancy. And the redundancy has to do with the fact that if I take the phi's, these are bosonic fields, I can move them around, and this moving them around sort of, or permute them around by some Sn permutation. And that Sn, when it affects these sigmas, it affects them diagonally. Because this phi, if I move these two phi's, you see, let's say there's a permutation from the 1 to the 2nd, that will affect the black lines, which go into sigma 1, as well as the red lines which go into sigma 2, and the blue lines. So that's why this is something that acts diagonally on the 3 sigmas. And likewise, there's another bosonic symmetry here and a bosonic symmetry here. Once you have the group action, this gauge equivalence, it acts on a set. The set is the triple of permutations. There's a very beautiful theorem in combinatorics which is called the Burnside lemma. You have a group H acting on a set S. You want to know how many inequivalent orbits there are for this group action. The Burnside lemma says the number of orbits is given by 1 over the size of the group. So in this case, the group is Sn left and Sn right, so n factorial square. And then sum over the number of fixed points of the group action. So what is the group action here? Fixed point, group action is Sn times Sn, so that's a double sum. What is that group acting on? It acts acting on triples, sigma 1, sigma 2, and sigma 3. What does it mean to have a fixed point? It means that gamma 1, sigma 1, gamma 2 must be the same as sigma 1. So this, in other words, this delta function is satisfied. Gamma 1 sigma 2, gamma 2 is the same as sigma 2. Basically, this follows, this equation here, these delta functions follow directly from what I said about the equivalences. There's an equivalence here. That equivalence directly dictates what is the counting, and the counting is given by the conditions that sigma 1 is, sigma 1, sigma 2, sigma 3 is left fixed by the action of the gammas. So if I take sigma 1, I act with the gammas, I get back sigma 1. In other words, this product multiplies to 1. So this delta is directly implemented Burnside lemma fixed point statement. Okay, so you naturally are led to these delta functions on the group. And then a bit of manipulation of this delta function tells you how many gauge invariants you have. It says you sum over partitions of n, you take the symmetry factor of that partition, and that is the counting of invariants. What is the symmetry factor of the partition? Well, we said the partition had 1 to the sort of a number of 1s, a number of 2s, a number of 3s. So P1 1s, P2 2s, and P3 3s, and so on. So there's a formula in terms of the P's. What is the symmetry factor of the permutation? And that is the number of invariants. So just do a sum over partitions, and it follows directly from the permutation equivalence.
So what techniques do you have in computing those delta functions?
So basically, after a little manipulation, so there's a little bit of, I mean, there's kind of standard things. A physicist sees a bunch of delta functions and some sums they would solve for the delta function. You know, for example, here you solve for gamma 1 in terms of gamma 2. So then you get rid of one delta function, and then everything will involve now gamma 1. And then since this, if you, for example, if you just have one of these delta functions and have a gamma 1 here, you know, this symmetry factor basically is, by definition, that symmetry factor is gamma sigma gamma inverse equals sigma. So if you give me a sigma which has a certain number of 1 cycles, 2 cycles, and 3 cycles, and so on, specified by partition, 1 to the P1, 2 to the P2, and so on. And I said, how many gammas satisfies this equation? How many gammas leave it fixed? It's that sim P. So basically, from the deltas, in a few steps, you get to that.
Are there any analytic formulas for this?
Well, I mean, okay, so, you know, so this kind of formula, you can get Z3 of n, let's say, up to n equals 15 or 30 or whatever. If you want a generating function, that's a good question. I don't know. That'd be nice to find. So you can, this is easy to work out. At high orders, you can do this with Mathematica. These are the kinds of numbers you get. And then if you want to count connected traces, or connected invariants, which are the analogs of single traces. So you can 5 bars, you know, there are these lines connecting 5 and 5 bars. If you want to have connected composites of 5, there's a nice way to do it using using plethistic logarithms, which have been used in Army's papers in supersymmetric gauge theories and so on. So you can compute, you know, write out this thing, write out the generating function for this up to some order, let's say 30, and then there's a formula, the plethistic log. You apply that thing, and then you get the connected ones. So there's nice ways to get the connected counting as well. And if you go to general rank D, you'll have sigma 1, sigma 2 up to sigma D, manipulate the delta functions. This is what you get. You sum over partitions of n, sim p to the power d minus 2. So in the case of d equals 3, we had sum over the sim p. Now we just have sum over sim p to the power d minus 2. And some open questions, as was already hinted by Ami. Would be nice to find, you know, this ZD of n is some number, some sequence with some fairly concrete formulas. Let's build a generating function, ZD of n x to the n. Might be useful to build a kind of a, these numbers grow very rapidly, by the way, because it's like typically in matrix theory, you get, let's say the one matrix problem, you get a counting where you're summing over partitions of n with weight 1. So d equals 2, which is kind of the matrix case, you get sum over p. Here you get sim p to high powers, and sim p itself contains factorials. So this grows very rapidly. So in order to build a generating function, you may want to divide things out by n factorial to some power or something. And then you want to know what is this kind of function. So that's a very nice question. If you have an idea how to compute this, I think it would be interesting. And using these generating functions, one would like to find asymptotics of these numbers. And similar kinds of sequences have been studied recently in the context of thermodynamics or tensor models or tensor field theories. There's similar kind of growth. These numbers have been studied in Beccarian cycling, and some asymptotic estimates are in a latest paper by Klebanov using some numerical estimates. But I think there are also techniques in cycling papers having to do with integral equations and so on, which might help find these asymptotics. But I think it's a very interesting question. Now, as we saw in the simplest case, there's always a counting with permutations and a dual counting with representations. So what does a dual counting with representations look like? So, actually it turns out this is related to a very fundamental problem in SN group theory. So, you take a Young diagram R1, a Young diagram R2 and R3, take the tensor product of them. Each of them is an E-rep of Sn. Let the diagonal of Sn, so let's the diagonal Sn act simultaneously here, here, and here. Sigma, tensor, sigma, and sigma. Let it act on this thing. That's a representation of Sn. How many invariants in that action? That number is called the Chronicle Coefficient. C, R1, R2, R3. Chronicle Coefficient is very interesting for mathematicians because, the Littlewood-Richardson coefficient is a more familiar number we work with all the time. Combine Young diagrams and then it computes for UN tensor products. And that's a nice thing. It's a multiplicity of a representation, so it's a positive integer. But there's also a constructive way to do it. Put together Young diagrams according to a certain rule and you'll get that number. This is also a positive integer, or 0. And mathematicians want to know whether there is a constructive way to do something to count that number, just like for Littlewood-Richardson coefficients. And this question has been around for 100 years, and there's no complete solution. There's some partial limiting case solutions or whatever. But is there a constructive way of finding this number? And that's a very interesting question. Turns out that for tensor models, if you count the Z3 of n, you get exactly this number, sum of squares. So in fact, there is a constructive way of counting the sum of squares, is to count tensor model invariants. It doesn't answer the old question, how to count individually C, R1, R2, R3, but the sum of squares can be counted just by counting tensor model invariants. And in this formula, the finite end cutoff, for reasons that I described before, is very easy. The height of these Young diagrams should be no higher than n, this has nice consequences which have been explored in a couple of papers that I've described here. So sum of squares is very interesting. And the sum of squares is related to, what it is saying is that it's related to the structure of algebras. So you have triples of permutations. You have this equivalence by left and right multiplication. You can say, now let's go to this vector space. So this is a tensor product of vector spaces, where I take sigma 1, tensor sigma 3, tensor sigma 1, tensor sigma 2, tensor sigma 3, allow myself linear combinations, that's a vector space. In that vector space, I ask myself, what is the subspace which is invariant under the diagonal left and the diagonal right? That subspace, you can show, is an algebra. It's a semi-simple associative algebra. And therefore, its dimension should be a sum of squares, as we just saw, that the number of these equivalence classes is a sum of squares. And therefore, there should be a nice representation theory basis, which is going to be labeled by 3 Young diagrams, with each time you have a triple of Young diagrams with non-vanishing Chronicle coefficient, there should be that many squares of elements in this algebra. So basically, that's what this formula says. You take this triple of Young diagrams, and I and j run from 1 up to this Chronicle coefficient, you expect a matrix basis for this algebra. And using group theory, you can construct this, Clebsch-Gordons and matrix elements, and you can construct what this group algebra element in here, which lives in this subspace, which is invariant, and that's as expected from this structure theorem. And so there's a matrix type multiplication in blocks. So this IJKL has delta JK, QIL, that's the matrix structure. Blocks means that there's one block each time you have a triple with non-vanishing Chronicle coefficient. And if you have another triple with non-vanishing Chronicle coefficient, the product is 0 unless these two triples are the same. These are the deltas. So that's why I say matrix blocks. These are matrix structure and this is the block structure. If this triple is different, this times that is 0. Okay, so matrix block. And so basically we have a basis for this K of n algebra, which is a linear combination of sigma 1 tensor sigma 2 sigma 3. There's some formula for this, not too interesting, but you can build it. And each sigma 1, sigma 2, sigma 3 is a way of contracting indices, so it's an operator. So for this linear combination, we also have an operator made out of phi and phi bar. What are the nice properties of these operators? Well, if you compute the two-point function in the Gaussian model for these operators, which depend on triples of Young diagrams, basically, this is a kind of a normal ordered correlator, which means that when I compute this by Wick contractions, I only allow Wick contractions from here to here, but not within this guy. And if I do that, two-point function, normal ordered operators, this is a diagonal two-point function. All these labels have to be the same here and here. So finding orthogonal bases for gauge invariance is important and interesting for the physics, as we know from ADS-CFT, and this group theory way of thinking about invariance continues to give you orthogonal bases for the tensor case. And this result was arrived at in a few of these parallel papers that I mentioned before. So it's a good time to pause maybe for questions. And a small trick, and then I'll continue. Great. Now there's even more fun combinatorics you can do. So, what exactly does this invariance look like? So for n equals 2, in that sequence I showed you, there was sim, so we have to look at the partitions of 2. So 2 equals 2, or 2 equals 1 plus 1. 2 equals 2 means a cycle of length 2. So that has a cyclic symmetry of 2. This cycle of length 1 and cycle of length 1, there's a 2 factorial, so 2 plus 2 is 4. So directly from that formula, you know there are 4 invariants. What do they look like? One of them looks like, basically we're contracting phis and phi bars, and there are 3 kinds of indices, black, blue, and red. So you can have a disconnected diagram like this, phi with phi bar, phi with phi bar. And then you can have connected diagrams, where a pair of phi and phi bars share 2 legs, phi and 2 legs, and then this pair and that pair share 1 leg. But then the 1 leg shared could be black, blue, or red. So there are 3 kind of diagrams, which are kind of related to each other. Although there are 3 of them, they're actually related. So would it not be nice to count them as 1, so that once I have that, I just kind of reorder the colorings and I get the others? So that was another question that Joseph raised. So the question was, how do you count these gauge invariants in a way that treats these diagrams, which are related by color exchange, as equivalent, as the same diagram? How would you count that? Because it's practically a very useful thing to do. Well, color exchange, you can also describe very nicely in terms of these permutations. You have these triple sigma 1, sigma 2, sigma 3. Basically, I can introduce a new equivalence where sigma 1, sigma 2, sigma 3 is equivalent to sigma 2, sigma 1, sigma 3. or any 3 factorial reordering. So you can count with this extra equivalence when you are reordering these sigmas. And again, you apply the same Burnside lemma stuff. You can get a formula in terms of delta function, and there is a new sequence. It's the counting of invariant gauge invariants of U and Q, where we are treating these kinds of diagrams related by color reordering as identical diagrams. So I just want to count the orbits under this color exchange symmetry. So you take this, there is a formula for this again. You have 1/6 now is a fraction times the same sim p that we saw before. And then you have something else. 1 over n factorial, this guy, 1 over n factorial, or this 1/6, 1/2, 1/3. What is this number? It tells you, given any let's look at Sn permutations. Look at it in an equation. Gamma cubed equals sigma cubed. So let's say gamma, let's think about the equation. Gamma cubed equals sigma cubed. So how many permutations? Take all pairs gamma and sigma. Ask yourself if gamma cubed is equal to sigma cubed. Find how many pairs satisfy that equation. So that number, the number of gamma cube, sigma cube, the number of solutions to that equation in Sn is a number. That number appears here. You divide that number by 1 over n factorial, so you get something. And then there's something similar here, and there's another number here. If you add them with coefficients 1/6, 1/2, 1/3, you get the desired counting of graphs up to color symmetrization. So, and the 2 we know, we should get a 2, because here there is 1 graph, and these 3 are the same up to color reordering. So we expect 2. Great. So we now have a formula which reproduces these 2, but makes sense for any n and any number of phis and phi bars. So you can develop this sequence. And as we were developing this sequence, along the way, we observed this curious fact that this number by itself is an integer. And this number by itself is an integer. In other words, the number of solutions to gamma cube equals sigma cube is always a multiple of n factorial. We didn't know this. We hadn't seen this anywhere. And so this was an experimental observation that these things separately are integers. They are integer sequences. So there's a surprising integrality that appears. So this was one of the things that motivated us to revisit this counting problem recently. And actually, the upshot was that you can actually prove that these 3 are integers. And you can prove it by, again, thinking about algebras. Think about this permutation algebra, C of Sn, tensor C of Sn, tensor C of Sn, which is the subspace which is invariant the left and right. That's an algebra K of n. But you see, this left action and this right action, they commute with this S3 action of permuting these 3 things. So actually, even after you've modded out by the diagonal left and the diagonal right, you have an S3 action. So you can take this algebra and decompose it into the part which is symmetric under S3, anti-symmetric under S3, and mixed symmetry. So each of these representations of S3 in this algebra will appear a certain number of times. So there will be 3 integers in the game. How many times does this appear in this algebra? How many times does this appear? How many times does that appear? So there are 3 integers. Using that integrality of 3 integers along with integrality of S3 characters, you can prove that these 3 things are integers. So that's kind of interesting. There's a kind of a non-obvious integrality having to do with solutions of equations in permutation groups, and that integrality can be proved by thinking about permutation algebras, which are inspired by tensor models. And this kind of thing and this integrality generalizes for rank D tensors. You can do this with any number of SNs, which has to do with tensors having D indices. Great. So that was some nice mathematics associated with this counting of tensor invariants. Let me talk a little bit about some of the kind of physics of this. So aside from counting, the next thing we want to do is look at correlators. So let me look at correlators of a complex matrix model. So I have, this can be a kind of a warm-up, which will lead to the 3-index tensor model things. So we have invariants of one matrix, labeled by a sigma, and the sigma is produces the same gauge invariant operator as gamma sigma gamma inverse. That's the conjugation equivalence we talked about. And now what happens if I take these two observables and put them in the Gaussian integral and calculate the correlator? Turns out the correlator is some function of sigma 1 sigma 2. Okay, and you can, there's going to be a sum which has to do with the width contractions. This gamma sum has to do with the width contractions, sum over Sn. So this is made out of n copies of z's, n copies of z dagger, width contraction of z and z dagger. There's a thing here. And then so there's a formula that you can write in terms of these permutations for the correlator. And essentially it boils down to calculating, take sigma 1, take all permutations in the conjugacy class of the first one, all permutations, sum of all permutations in the conjugacy class of the second one, the cyclostructure of the second one, and then take a third permutation, sum over everything, impose that the product is 1, and then weight it by n to the power of the number of cycles in this guy. And that gives you a formula, purely in terms of permutations for arbitrary products of traces of z, correlated with arbitrary products of traces of z dagger. So this is very interesting. Delta, sigma 1, sigma 2, sigma 3. So we're counting triples of permutations which multiply to 1. So there's a beautiful geometry behind this, which was studied back in the 90s when people were investigating the string dual of two-dimensional Yang-Mills theory. So basically, what the geometry behind that counting is that if you think about a sphere, in this case, take an S2, and think about covering spaces. So world sheets which cover S2. One cover is that, you could just have a world sheet that covers S2 once, another one separately covers it twice, separately a third one, and so on. So you have you can have n distinct, disconnected covers. Or you could have some way of mixing these different sheets in the cover. And one way to do that is to have branch points in the covering map. And if you have 3 branch points, then as you go around the first branch point, you follow the inverse image of this path, and then you go there, you come back. You might come back with one move to somewhere else. So there might be a permutation. So when I'm counting branch covers of the sphere with 3 branch points, there will be 3 permutations which tell me how the branch point mix the sheets of the cover. And there's a condition that if I follow a path that goes around all 3 of them, that's a path that is contractible. I can wind it around the back of the sphere and shrink it. So, 5 minutes. Oh, sorry, yes, I was counting wrong. Right. So good. So you have this counting triples of permutations is the same as counting branch covers. And if you do a little bit of manipulation, normalize these things correctly, we are actually counting maps from some surface to two-dimensional sphere, which is branched over 3 points, such that the branching over 2 of those points is determined by the observables that you put in, and the branching over the third one is arbitrary, and the branching over the third one will determine the genus of the cover, and this can be shown to be equal to basically a sum over these maps with n to the power of the Euler character. So we just started with Gaussian complex matrix model and computed correlators. It's counting maps from two-dimensional wall sheets to an S2 with specified branches. And the way the power of n appears is suggestive of G string equals 1 over n. So this is there's an emergent S2. So this story with the complex matrix model was done actually in a paper by Tom Brown, one of my students around 2010, which followed an earlier paper around the same time with me and Robert, where we did the Hermitian matrix model case using similar combinatorics and similar geometry. And this kind of follows the tradition of work of Gross and Taylor, who established a 2D string picture for 2D Yang-Mills gauge theory. What is interesting here is that, in the 2D Yang-Mills story, there was a target space, which is a 2D surface, and then you had a string with that target space. Here, this is a kind of zero-dimensional Gaussian matrix model, and yet you see an S2 coming from the combinatorics of the counter. What happens if we do this with a complex tensor model? First of all, if you just count the 3 index tensor model observables, just counting at this point, this is Z3 of n that I showed you, you can rewrite that as counting triples of permutations subject to multiplying to 1. So you're counting branch covers of S2 with 3 branch ones, which also tells you that the counting of observables in the complex matrix model is related to correlators of the complex matrix model. So this is tensor model observable, just counting of observables. It's related to similar kind of thing as here, a correlator of complex matrix model. So it gives you a relation between tensor models and matrix models. So here's a question. To summarize this, if you sum over correlators in the complex matrix model with arbitrary hollow and anti-hollow observables and take the limit of n goes to 1, n goes to 1 was needed because you get powers of n here. Take that limit, you get the counting of observables in the complex 3-index tensor model. So here's a question, what is the interpretation in terms of dual space-time physics? Complex matrix model is related to half BPS sector of ADS5 CFT4, tensor model potentially related to ADS2. So what's the interpretation of this connection between complex matrix model and tensor model? And this kind of formula generalizes to rank D tensors as well. Okay, so this was just about counting of observables in the tensor model. What about correlator? Take something made out of 5 and 5 bars. It is labeled by 3 permutations. Can we express that geometrically? Well, here it is. You have this thing. Turns out that you can. There's always a sum over weak contractions, gamma Sn, having to do with contracting the 5s with the 5 bars. And these are the delta functions that you're getting. So you're counting a whole bunch of permutations subject to some conditions that some products multiply to 1. So it's a very generic thing that whenever you have, sort of sums like that, they are kind of counting. You can associate to that. You can associate to this a counting where each of these permutations is associated with a path in a 2 complex, and the conditions that certain things multiply to 1 has to do with certain paths forming closed cycles. So like here, if I identify this point and all these points are identified, so if I go, this is a closed loop, A to A, another closed loop, this condition, gamma sigma 1 alpha 1, it kind of spans a triangle, and that path is contractible. So from this I can read off a kind of surface, or a 2 complex, such that coverings of the 2 complex are counted by these sums. Okay. And so from here you can read off, and it turns out the powers of n always work out if you normalize observable rightly, so that you get Euler character of this covering surface, or the covering 2 complex. So from this structure, these delta functions, what you find is you have 3 triangles joined at one edge, because the gamma here is shared by the 3 delta. Each delta is a 2 cell, and the same gamma appears in all 3 of them. There are three surfaces meeting at an edge. Now this cannot happen in 2 dimensions. 2 dimensions, if you triangulate a 2-dimensional surface, every edge will be shared by at most two kind of plaquettes. So at most 2. Here you have 3. So this can happen in 3 dimensions. I could fill this up with so there's a 1 cell, a 2 cell here. I can cover it up and fill it up with a 3 cell, and I'll still get the same counting. Because the counting only cares about 1 cells and 2 cells. But fill it up with higher cells, doesn't matter. So the point is that this guy is not a smooth 2-dimensional surface, but it can be a smooth 3-dimensional surface. And if you look at higher rank tensor models, you always get something like this. Multiple triangles joined here, which can be a smooth 3-manifold, but they cannot be a smooth 2-manifold. So, and you always get counting of coverings of these kinds of complexes with the right powers suggestive of a sort of stringy interpretation. So these 2 complexes cannot be part of a smooth 2-manifold. It can be of a higher manifold. It's interesting to compare this with this, what people were trying to do with this tensor model community. They were kind of inspired by 2D gravity matrix model connection. They were trying to generalize this to higher dimensions. So in a sense, there's something going on here which is suggestive of higher dimensions. But what's also interesting is that no matter how high the rank goes, you still get a 3D target, according to this picture. So this suggests that there's a 2D topological string with a 3D target which underlies the combinatorics of counting and correlators for the rank D tensor models. And some aspects of the counting in particular are captured by a 2D target, like I showed before. The counting of observables was counting covers of a sphere with 3 branch points. So I think this is an interesting thing to explore. To summarize, permutation algebras provide a unifying framework for matrix and tensor models, counting and combinatorics of general things in Gaussian models at least. Can be done neatly using these algebras. Would be nice to make more direct contact between this algebraic approach and the SYK. In order to do that, one would consider, here I took Gaussian model, general observable. A particular observable would be an exponential of the quartic interaction. So you take that particular observable and you could study its correlators using this kind of technology. And one could try and make contact with this double scaling limit that people have studied. That's an interesting direction to think about. Also, what's interesting about this story is that this permutation algebras way of looking at invariants gives you always, because these algebras turn out to be associative and semi-simple, they give you some underlying matrix structure. And it's a matrix structure not really direct related to indices of the phi, but having to do with the structure of the permutation algebras. And this matrix structure, people have studied, kind of these algebras which are called Frobenius algebras, which are related to 2D topological field theories. Nice associative algebras. This kind of algebraic structure is studied in the context of CFT2 and brains. And actually also in Alberto's talk there was algebras and modules are related to brains. So this kind of hidden algebra structure is related to brains and kind of string interpretation. So this is suggestive of a common stringy structure in matrix and tensor models. And another common stringy structure comes from the connection between permutations and branch covers. And there are many interesting links to combinatorics, some of which I have hinted at. I'm going to mention one more. That second term in that 3-term sum I wrote, which I said had a surprising integrality, you can also write it basically as the sum of entries in the character table of Sn. So R runs over all representations of Sn. This is every conjugacy class. Take all the entries in the character table, you sum it, you get that thing which was the second term, which was mysteriously an integer. Well, at first sight anyway. This we know should be an integer. In fact, it is also known that if I do the sum over arbitrary cipher structures for fixed representation, this is also a positive integer. I mean, the characters can be positive or negative, but this particular sum, you can show, always has to be a positive integer. just from group theory stuff. And it is an open problem that Stanley stated among some list of open problems. So a lot of the time what these representation theorists or representation theoretic combinatorists are interested in is that some number which you know is positive, is there a nice constructive combinatoric interpretation, just like for the Chronicle coefficients. So this is one of these open problems, to find a nice constructive combinatoric construction which produces this number and thereby shows that it is a zero or a positive integer. So from tensor models, you don't quite have this, but you have this sum over representations. And that has to do with counting tensor model observables, subject to color exchange, and so on, which we described. And one question is whether you can refine that story and approach this kind of sum of character table for a fixed representation. So I'll stop here.
Any further questions? Yep.
Yeah.
Group theory decompositions in terms of the permutation group. Some previous question. I just wanted to know. In 2 plus 1 dimensions,
Yes.
you have particles. They have analytic statistics. They fall into different representations of the permutation group other than the symmetrical.
That's right. Yeah.
Higher dimensions. About 2 spatial dimensions. So I am still a following problem. Is there any simple way to know when I tensor product, say suppose I have a UN group, the tensor product P fundamentals and 2 anti-fundamentals. I'm considering an n particles having P plus Q is n.
Yeah.
If I have a tensor product in that, how many singlets will be there in this tensor product? Is it possible?
Sure. Yeah. Basically, if I understood the question correctly, P has to be equal to Q, and the answer is P factorial.
So there's a simple answer.
Yeah, that one has a simple answer. But maybe your physics question might be related to something more complicated. But
so what I wanted to say is that suppose I had as long as I keep n bigger than a certain number of particles.
yes.
Okay, so
Oh, sorry. So the answer I just told you is the correct answer as long as rank n is big enough. If rank n is smaller, then there's a modification of that answer, I think.
So suppose I did a 3 fundamental scan.
Yes.
Fundamentals in 3 fundamental particles as 3 element scan.
Yeah.
So in the group theory space, in the color space of 3 fundamental particles, as long as n is bigger than 3, I have no sequence.
That's right. Yeah.
But if n were to be 3, I have 1 singlet.
Okay, good. I think this can be done with these methods. We can talk about it.
Okay.
I think this can be done.
Other questions?
I can ask about this 2-point function that
Yeah.
you might have a way to calculate that.
Yes.
In some other studies of these models, they have this mnemonic diagram, so
Yeah.
they seem to dominate
That's right.
large n. Do you see any? Your calculation would be exact for all n.
That's right. Yeah. So I think this is sort of it's a good question. One would want to take the Gaussian model, perturb it with a particular quartic interaction with a coefficient, and take a scaling limit of that coefficient. So basically, this method will give some formula for that, some exact formula for that correlator, because it's an exponential, it's an explicit thing. We just have to take that observable and express it in this permutation language. And then it will give some formula. The question is then to recover this melodic dominance in that double scaling limit. You'll have some group theory formula. How do you make that connection? I think one should try, because there are some arguments that this melodic dominance happens. So one would want to translate it. And then hopefully this will give us a way to go beyond this melodic approximation.
Any other? No further questions? So thanks, Sanjaye.